So, we spoke about graphs last time. So, let us study in a little bit more detail what walks on graphs look like. Okay, so recall what a walk was. So, let us draw a graph. So, I have some vertices and some edges. So, here is an example of a graph with 6 vertices, which we will number as 1 through 6. So, let us call these 1, 2, 3, 4, 5 and 6. So, here is our graph, and what we are going to do is to try and count walks of various lengths on this graph. Okay. Now, let us focus on these 2 vertices 1 and 2 and ask ourselves how many different walks are there of various lengths. So, here is want to start at 1 and stop at 2. So, let us count walks between these 2 vertices. So, there are various lengths of walks. So, let us also keep track of the length. So, recall the length of a walk is just the number of edges that you travel across when you go from one vertex to the other. So, here is a walk of length 1, you just start at 1 and you go to 2 along this edge. So, there is just one way of doing this. So, I am going to count the total number of such walks. Okay, there is no other way of going in just one step or with length 1. Now, if we look at length 2, then there are lots more possibilities. So, we could go from 1 to 2 in 2 hops by, for example, traveling through 4 or 3 or 5. So, here are 3 possibilities and those are the only ones of going in 2 steps. Now, let us look at hops of length 3 or walks of length 3. So, even though it does not look like there is a path connecting 1 to 2 of length 3, we are only looking at walks rather than paths. So, here is a possibility you could go from 1 to 2 back to 1 and back to 2. Okay. So, you can just do this back and forth. Now, likewise there are sort of 4 other possibilities. You could go to 4 back to 1 and then to 2, 3, 1, then to 2, 1 to 5 to 1, then to 2, and then finally 1 to 6 to 1 and then to 2. So, there are sort of 5 possible, you can look at these 5 edges which are emanating out of 1. You can travel along any one of them, come back to 1 and then go to 2. So, there are 5 possibilities. These are not all. So, let us say 5 for a start. Similarly, you could do the following. You would go to 2 first go to 2 and then observe you can do that back and forth hopping even from 2. So, for instance, we go to 2, then to 4 and then back to 2. So, you first go to 2, then go to 5 and then go back to 2. Okay. So, likewise go to 2 and then go to 3 and then back to 2. So, there are sort of 3 edges coming out of 2, you can do this back and forth hopping along each of them. Okay, and you can convince yourself that that is pretty much the only ways of going from 1 to 2, a walk of length using a walk of length 3. Okay, and it gets sort of progressively more complicated as you try to compute walks of larger and larger lengths. So, what one usually wants when one has a graph like this is some way of calculating how many different walks there are to go from some starting point to some ending point, some vertex 1 to some other vertex 2 in this case, just traveling through the edges of the graph. Now, to do this, it turns out there is this rather nice method. So, let us define this notion. So, we somehow need to encode the various edges of the graph. So, let us put our graph here again. So I am just going to keep track of the various edges in this graph by means of a table, if you wish, and this table is sometimes called the adjacency matrix of this graph. So here is our graph G. So what does adjacency mean? Adjacency just means, we just keep track of which vertex is adjacent to which one, or in other words, which is a neighbor of which. The adjacency matrix will turn out to be a table with 6 rows and 6 columns. So let us draw some rows and some columns. So I have 6 rows and 6 columns. So we think of these 6 columns as being labeled by the 6 vertices 1, 2, 3, 4, 5, 6. Likewise the 6 rows. And we put a 1 in a box if, in the ith row jth column, if the vertex I is connected to the vertex j. Okay, so in this case what we are going to do is, for example, so 1 is connected to 3, 5, 6 and it is also connected to 2. So I also put a 1 there, and it is not connected to itself, so I put a 0 there. Okay, so the first row of my table tells me all the neighbors of 1, or the adjacent vertices to 1. Now likewise we look at 2, and 2 is connected to 4, 3, 1 and 5. So to 4, to 3, to 1 and to 5 and to nobody else. So we put zeros there. So let us complete the remaining boxes. So 3 is connected to 1 and to 2. 3 is connected to 1, to 2, to nothing else. 4 is connected to 1 and 2. 5 is also connected to 1 and 2. 6 is connected only to 1 and to none of the others. Okay, so this table, 6 cross 6 table that we completed, keeps track of what the various edges of the graph are. Okay, and this is called the adjacency matrix of the graph, and let us give it a name. It is called A. Okay, now in a sense, if you know the adjacency matrix, you know the graph. You can just reconstruct the graph by drawing the edges. If there is a 1 in the ith row jth column, you put an edge between I and j, otherwise you do not put an edge. Okay, now what does the adjacency matrix have to do with trying to count walks in a graph? Now notice that it is really a table in some sense, but we called it a matrix. So we want to think of this as really being a 6 cross 6 matrix rather than just a table with rows and columns. So there is something that one can do with matrices that is rather powerful, and which is what allows us to count these walks on a graph. So recall, what is a matrix? Well, a matrix is in a sense the same thing as a table. So if you had a 2 cross 2 matrix, for example, it would just be a table with 2 rows and 2 entries with numbers in them. So I am sure you have seen these before. You have two rows, 2 columns, 4 real numbers A, B, C, D in them. That is a matrix. Now the reason why matrices are rather important is because there is this very interesting operation on them, which is called matrix multiplication. In other words, you can multiply 2 matrices. So I am going to do that here. So I am going to take A, B, C, D and try to multiply it with another 2 cross 2 matrix E, F, G, H. And the rule for matrix multiplication, in case you have not seen it before, is the following. In order to find each of these entries, so here is the first entry of the matrix, this is the first row, first column of the resulting matrix. So the resulting matrix is again going to be 2 cross 2. So to find the entry in the first row and the first column of this matrix, you sort of look at the entries in the first row of this matrix and multiply it sort of term by term pairwise with the entries of the first column of the second matrix. So here I have got AB in the first row and EG in the first column. I multiply them together in the following way. So this entry here is going to be A times E plus B times G. Okay. Now, I do the same thing when I want to compute the entry here, the next entry. This is the entry in the first row and the second column. So, I take the first row here, which is AB again, but now I multiply it element by element pairwise with the entries of the second column of the second matrix. So, this now becomes AF plus BH, okay, and we do the same thing to the bottom. So, now we have to look at the second row and first column in order to get the 2 1th element, and so that is nothing but CE plus DG, likewise CF plus DH. Okay, so this is somewhat strange if you have not seen it before, but it is a completely natural operation in the world of matrices, and the matrix multiplication operation becomes rather interesting when you apply it to the adjacency matrix of a graph. Okay, so let us just try and see how we would do this to the adjacency matrix that we wrote out here. So, this operation of matrix multiplication becomes rather interesting when you start applying it to the adjacency matrix of the graph. For example, let us take the 6 cross 6 adjacency matrix that we have. So, all I have done here is now written that matrix next to itself. So, I am going to try and calculate the product. So, this is the adjacency matrix A times itself. So, I am going to do the matrix multiplication of A with itself. So, the thing I showed you here is the product of this 2 cross 2 matrix times the 2 cross 2 matrix EFGH. Now, we will do just A with itself and try to see what the different elements of the answer will look like. Okay, the answer is now going to be a 6 cross 6 matrix, but I am just going to be interested in just one of the entries for the moment, which is the entry in the first row and second column. So, let us look at, so there are 3, 4, 5, 6 entries. Likewise, it is a 6 cross 6 matrix. So, it is a 6 cross 6 matrix, but let us focus on this particular element here of this 6 cross 6 matrix, the one in the first row and in the second column. So, how does one obtain this element in the first row, second column? So, recall how matrix multiplication is defined. You are therefore supposed to scan through the elements of the first row of this matrix and pairwise pair them up with the elements which you get from the second column of this matrix, okay, and you are supposed to add them up in this way, AE plus BG or whatever it is that we did earlier. Okay, so let us do the same thing here. Now, I will keep track of my answer to see how I get it. So, observe that when I scan through the first row of my table, I am going to get first a 0 because somehow it tells me that 1 is not connected to a 1. So, I have a 0 there. Okay, I have a 0 there and I have a 1 here. So, this entry, we call it X, becomes the following. It is 0 times a 1, okay, that is the first term of the answer, plus a 1 times a 0, so that is the next contribution, plus a 1 times a 1, this times this, that is 1 times 1 again, plus the next term is a 1 times 1, and the last term is 1 times a 0. Okay, so, if I add all this up, I get 3 into 1, so it is a 3 total. But let us see how these terms, these individual terms were formed during the process of matrix multiplication. So, what we did here is to say we sort of paired things up in the following way. So, I had 1, okay, that is this row number, and I looked at among these column numbers 3, 4, 5, 6. So, there were 3 contributing terms, right. These are the only 3 which gave me 1s, all the other terms gave me 0. Which of these terms actually gave me a 1? Well, the ones corresponding to the following that, so let us look at these ones here. So, where did I get ones here? In the first column, in the first entry, there were 4 of them actually. They were in the neighbors, they are precisely the neighbors of the element 1. So, I have got 2, 3, 4 and 5 were exactly the 4 neighbors of the vertex 1. So, those 4 neighbors were exactly the ones where I will see a 1 in the first term, okay, in the first term of the product. In the, sorry, there was also this guy 5, there is also 6, 6 was also a neighbor. So, I also get a 1 there. Okay. And now, I look at the second term in each of the products. So, I have got, where do I see 1s in that? So, let us look at these guys 1, 0, 1, 1, 1 and 0. Some of them are 1s, some of them are zeros. Which ones are 1s? Well, those are precisely the numbers which are neighbors of 2. Okay. So, if you look at how we got those numbers, they are exactly the numbers in the second column of this matrix A, and observe that is exactly all the vertices which are connected to a 2. Okay. So, on the one hand I have got these neighbors of 1, and on the other hand I have got the neighbors of 2, okay, and which are those? They are exactly 1, 3, 4 and 5. So, there are 4 neighbors 1, 3, 4, 5. Okay. So, this is really what we have on the 2 sides of this calculation. On the one hand, I have written all the neighbors of 1, and on the other side I have written the neighbors of 2. Okay. So, the neighbors of 1 are what you get when you sort of go across this row of the matrix. The neighbors of 2 are exactly what you see as you go down this column of the matrix. Okay. And when you sort of take this product and this sum to form this matrix entry, what you really are doing is the following. You are looking at each neighbor of 1, okay, and seeing if that very same thing also occurs as a neighbor of 2. Okay. So, for example, look at this particular thing here. I have a 1 which tells me that 2 is a neighbor of 1, but then I have a 0 on the other side which tells me that 2 is not a neighbor of 2. Okay, let us look at the next term. I have a 1 here which tells me 3 is a neighbor of 1, and then I have a 1 also here which tells me 3 is also a neighbor of 2, right. So, if you go back, what the original graph looked like was the following. I had 1 and I had 3 which was connected to both 1 and 2. So, in other words, having that vertex 3 tells me there is a path of length 2, there is a walk of length 2 in my graph. Now, similarly, the other contributions, I have got this 1 and 1 here which tells me that 4 is a neighbor of 1, 4 is also a neighbor of 2. Likewise, 5 is a neighbor of 1 and 5 is a neighbor of 2. Okay. So, in a sense, what this traveling along the row and the column is really doing for us is trying to pick out the walks of length 2 in this graph. Okay. So, each of these 3 terms which finally gave me a 3 as total, what these correspond to are really these 3 walks. So, from 1 to 2. So, this term here is going through 3. The next term here is just saying I can go from 1 to 4 and then 4 to 2. The next term tells me I can go from 1 to 5 and 5 to 2, and there are no other ways of doing this. Okay. So, this number here is exactly the number of walks from the vertex 2 to the vertex 3 of length exactly 2. Okay. So, let us write this down as a formal statement. So, the same sort of argument works in general. So, if you take the adjacency matrix, so here is maybe the proposition or theorem, you take the adjacency matrix of the graph, and you think of it as a matrix and you multiply it with itself, okay, A multiplied by A. This is usually denoted as A squared, matrix notation, and you take A square and you look at its ijth entry, the entry in the ith row, jth column, of this matrix A square is exactly the number of walks of length 2 starting at I and ending at j, at the vertex I and ending at the vertex j. Okay. So, we have sort of seen this more or less by example in this case, and what is interesting is that this generalizes in almost the exact same way. So, let me state the general theorem. If you want to count walks not of length 2, but more generally of some length d, then all you have to do is just take this matrix A and multiply with itself d times. Look at this matrix A power d. So, let d be any number, can be 1 or higher. Look at A to the d, then take A to the d and look at ij. This is just notation for the element in the ith row and jth column. This is exactly the number of walks of length d. Between vertices I and j. Okay, so I am not going to formally prove this, but here is a nice little exercise. Remember, we computed right at the beginning the number of walks of length 3 from the vertex 1 to 2, okay, and we said, well, 4 is already a bit too much of calculation, but here is what you can do now that we have a simpler way of doing this. We just look at this adjacency matrix A, it is a 6 cross 6 matrix that we wrote out, check that if you take A cubed, that is the number of walks of length 3, and look at the first row second column element, this should be 8, which is what we got by actual computation. And here is the next question, find how many walks there are of length 4. Okay. We could not do this by hand, but now that one can actually do this matrix multiplication, you should be able to figure out what this number is.